Hello again. Thanks for coming back for another exciting video. Well, I'm kidding about the exciting part, but seriously, thank you. This idea of the mole occurs again and again. It's super important in chemistry. It's very, very, very important. It's a kind of a weird word for a very important idea. It's introduced at the very end of our first chapter, and then again revisited throughout the first half of the text through especially chapter 10, but I need to introduce it now and get you thinking about it. So I know what a gram is. It's a unit of mass. That's a weird word here, stoichiometry. We'll come back and visit that again much more in chapter 10, but we know what a gram is. A gram is a unit of mass, weight on the scale and a balance in the chemistry lab. But what in the world is a mole? Well, a mole is simple to define, difficult to grasp, because it's such a large number. Well, when you think of atoms, you think of something very, very, very small. So let me take a very, very, very large number of them so that I can macroscopically in my hand on a balance in the laboratory think about, actually weigh that number of particles. A mole of particles is, oh gosh, I forgot to count, 602 billion or trillion particles. I call it the chemistry dozen. It's like, I know it's a way of counting number of particles. We don't count them directly, of course. It would take way too long. You'd be dead by the time you counted that many particles, even if you could count them 1 by 1 or 10 by 10. But I count them by weighing them. I weigh them on a scale. So here's another definition. If I think about the usual carbon-12 atom, carbon-12 has 6 protons in the nucleus and 6 neutrons. Also 6 electrons, but those electrons are so light. I'm going to define the mass of one carbon-12 atom to be, that's a definition, 12 atomic mass units. Now an atomic mass unit is a hugely small number. And again, we'll never be able to measure it directly in the lab. But there's a really weird thing, that this definition will help us carry over with the idea of a mole to something we can weigh. One atomic mass unit is about the mass of one proton or neutron. Not exactly, but very close. Alright, so we can't weigh such small amounts, but by considering this huge number, the mole number, we can actually count by weighing. So your typical periodic table has 2 numbers, and if you're lucky, a name, but not even a name. You should memorize the important ones like iron, chromium, vanadium, zinc, hydrogen, sodium, potassium, calcium. Every box has 2 numbers, and those 2 numbers are, one of them is a whole number, an integer. That's because gold is defined by 79 protons in the nucleus. But the other number is not a whole number. Usually it's a decimal or a fraction. It's the average mass of your average gold atom, which might not have the same number of neutrons. The number of protons defines gold, but the isotopes vary a little bit in the number of neutrons. Let's see, what's 197 minus 79? 100 and something neutrons? But again, that can vary from gold atom to gold atom. But here's the weird thing. This number is officially an atomic mass unit, but I can't weigh that directly. But if I take 1 mole of gold atoms, then indeed that mole would weigh 197 grams on the scale. And I'd be rich because gold is very expensive, very valuable. Every single element works exactly the same way. Carbon, element 6, on the table, 6 protons, usually 6 neutrons, but some of them may be 7 neutrons, some of them may be 8 neutrons. So if I take a pure sample of carbon, which is not always easy to find, but if I do, 1 mole of carbon atoms weighs very, very close to 12.0107 grams. That's why the mole is so important. It's also important because I can't compare masses in grams of each atom to each other because they all weigh differently. Gold weighs a lot more than carbon, which weighs a lot more than hydrogen. So because elephants weigh more than horses and dogs and cats and eggs, and they all weigh differently, all these elements weigh differently, I have to compare in moles instead of comparing in grams. So if I had water, hydrogen weighs 1.01, but you see here H2, 2 hydrogens. So I add 2 of those up and 1 oxygen, and the total mass is 18.02 atomic mass units. But I can't make use of that, but I can make use of the fact that 1 mole of water, that's 6.02 times 10 to the 23rd particles of water, has a mass of 18.02 grams. And that comes from the table, and that's added straight up from the periodic table. That is so nice and handy. So again, from the table, carbon weighs 12.01, and 12.01, and there's 4 hydrogens, and I add those numbers up. Here's 1.01, 1.01, 1.01, 1.01. I'm adding by multiplying, you know what I'm saying? Simple algebra. 1 mole of methane, although it would be hard to weigh because it's a gas, 16.05 grams per mole. And all these compounds and all the elements are different. They weigh differently because, once again, every atom has a different mass. Different number of protons, neutrons. Here's iron 3 oxide. Now I say 2 irons. Iron, iron, oxygen, oxygen, oxygen. Or do it this way, and you get 159, almost 160 atomic mass units. Or in other words, 159.687 grams for a mole. And that would, of course, take up different volumes than other compounds. Hopefully you see what I'm doing here. You see the pattern soon. 2 aluminums, 3 carbonates. That's a carbonate ion. But 3 of those has 3 oxygens and 1 carbon. So just be careful with the numbers in your math, but it all should work out. Here's a hydrated salt. Copper 2 chloride hexahydrate. That's 6 waters go along with that. We're not really multiplying here, but there are 6 waters along with that cobalt and the 2 chlorines in this salt in the bottle in the back room. Yeah, I think I have some of that. I could go get it, but who cares? It's a salt. It's dry. It's solid. I can weigh it. And I can weigh it on the scale. 58.93, that's cobalt, 2 chlorines, 6 waters. Water is 2 hydrogens and 1 oxygen. That all adds up to 237.95 AMU, atomic mass units. But I can't weigh that, but I can weigh this. So if I was rich enough to afford 240-ish grams of cobalt chloride hexahydrate, I'd have a mole of cobalt chloride hexahydrate. Caffeine's a powerful stimulant. Here's the molecule of caffeine. 8 carbons, 1, 2, 3, 4, 5. There's a carbon there. 6, 7, 8. Did I overcount? 1, 2. Anyways, if I'm right here, that's 8 carbons, 10 hydrogens, 1 nitrogen, 2 oxygens. 1 mole of caffeine would be a huge amount. We're usually talking about milligrams of caffeine in a cup of coffee or a Mountain Dew or something. Red Bull. Wow. Oh yeah, by the way, doesn't a mole of caffeine weigh less than a mole of cobalt chloride? And that weighs more than a mole of, 237. Wow. That cobalt chloride is about the same molar mass as aluminum carbonate, but certainly more than a mole of rust iron oxide. Well, I hope you're seeing the patterns here, the similarities, because here's why I care. Sometimes I can change grams to moles or change moles to grams. 152 milligrams of caffeine in a cup of coffee. A milligram is 1/1000th of a gram. So I move my decimal 3 places, 0.152 grams of caffeine. Then I put that number, I'm going to use these numbers up here that I've been calculating. I'm going to use that number of grams per mole as a conversion factor. Hopefully you've watched my video on dimensional analysis. So you kind of get a sense of, put the grams on the bottom, moles on the top. This gram cancels this gram. 0.152 divided by 194.922 gives me a very small number of moles of caffeine. Interesting. 152 milligrams is a small number of moles of caffeine. And you're still probably scratching your head, why do I care about moles so much? It'll become more apparent as we practice this more and more and apply this to this thing called stoichiometry. 127 grams of water. Let's take the molar mass of water. I calculated this above. 18 grams of water, 1 mole of water. The grams cancel. 127 divided by 18.02. 7 moles of water. Or 53.9 grams of methane. I can make up any number I want here, but I cannot make up this number. This number depends on the grams per mole ratio of carbon and 4 hydrogens. It comes from the periodic table. Interesting. Back to the cobalt chloride. What if a recipe I was using called for 0.075 moles of cobalt chloride? Well, then I would take this molar mass of cobalt chloride I calculated from above, put the mole on the bottom this time to get the mole to cancel, and multiply by 237.95, and that gives me 17.8 grams of cobalt, or about 18 grams to 2 sig figs. Yeah, 2 sig figs. So I can change moles to grams or grams to moles depending on what I need at the time. Here's 7.41 moles of aluminum carbonate. Maybe I need that in a chemical reaction or a bucket or a big solution for some reason. And I put the molar mass. I calculated this from above, so look up above and you'll see where I got that 234. That's 2 aluminums, 3 carbons, 9 oxygens. Adds up to a pretty heavy mass, molar mass. Grams to moles and moles to grams. You got to be able to do this. Of course, this is the first time you've seen this, so you're freaking out like, what in the world? I can't do that. But yes, you can. You just have to practice some. 1.105 moles of iron oxide. How many grams would that be? Well, I'll put the moles in the bottom, the grams in the top. Again, I got this from above. I added up 2 irons and 3 oxygens, and I got this number. So this one times this one, because it's in the numerator. Now here's maybe one last example of why this is so important. This is called a balanced equation. It says 2 Ni3s decomposes to give 1 N2 and 3 I2s. If I had 2 grams of Ni3, I really can't compare grams of this to grams of this to grams of this. They all weigh differently. So I change grams to moles by the same method we just saw above. Well, that's interesting. But then what I do is I take this, and I'm going to use it a little bit. You see this 2 here, used to balance the equation? That really means 2 moles. You can interpret it to mean 2 moles of Ni3. This is 1 mole of N2 and 3 moles of I2. So I can come up with these things called molar ratios, or mole ratios. I could say 2 compares to 1, or I could say 2 compares to 3. And you can also turn these upside down. Right side up, upside down, doesn't matter. What matters is you're trying to convert from one thing to another. Oh yeah. Oh, shoot, wrong way. And oops, one more. And also what I mean is this compares to this, but this also compares to this. But this might also compare to this. And there's 3 different things and 3 different mole ratios on that one. So one thing I could say is, again, if I had 2 grams of Ni3, what would that mean in terms of comparison to the other products? Well, I had 2 grams of Ni3. I've calculated the molar mass to be 395. Iodine is a heavy atom, and that would change my grams to moles. But what if I wanted to convert Ni3 into N2, or compare 2 grams of this to how many grams of this am I going to get? Well, here's the 2 to 1 ratio. 2 to 1, 2 to 1. I put the 2 moles of Ni3 down here because I wanted them to cancel, and I put the 1 mole of N2 upstairs because I want to convert into that. Lastly, this is a 3-step conversion. I'll put the 1 mole of N2 at 2 times 14 molar mass. The moles of N2 cancel, and my math would end up being something like this. This is a freaky example. I remember the first time I saw this, I'm like, what? But you'll get the hang of it. Do I have another example? I think I have one more example. Maybe time for one more, 1.5 minutes to go. Again, same reaction. 2 of these, 1 of these, 3 of these. 2 grams. I kept it at 2 grams Ni3. So here I did the same thing as before. I converted 2 grams of Ni3 into moles of Ni3. But then I put 3 moles of I2 on the top, trying to discover how much I2 I would get, iodine I would generate. And iodine weighs, there's 2 iodine atoms in an I2, so 2 times that. And my math would be something like this: 2 times 3 times 2 times 1.2, or 127, divided by 392, and also divided by 2. But if you're smart, you see the 2's cancel. 2 times 3 times 127 divided by 395. Looks like it comes out to 1.94 grams of iodine. You see, there's no way to predict from 2 grams of this, how much of this I would get. There's no way to predict without going through this. I call it a 3-step conversion thing. I think I am just about out of time. Oh my goodness, I had a whole bunch. I had 3 more pages. Oh well. See you in class. Thanks, guys.